In this presentation, I hope to explore if Mario Kart is fictional or fictional. So Mario Kart is one of the most beloved games of young kids, families, and gamers alike. According to Wikipedia, Mario Kart 8 Deluxe is first in tier for being the best-selling Nintendo Switch games, with over 57.01 million copies sold as of September 30th, 2023. Additionally, with a total of 36 different playable characters in Mario Kart 8 Deluxe and a lot of different vehicles to choose from, as well as tires and gliders, it is overwhelming to choose the best combination. Does Mario Kart follow expected physics laws, and what variables impact the speed of the player as well as the acceleration? In the top left, you can see that the car is going around a curve that is on a slant. This force diagram shows that the weight of the car acts vertically downward and that this force can be broken down into two components, one parallel to the surface of the ramp or normal force and the other perpendicular to the surface. Additionally, the normal force acts perpendicular to the surface of the ramp and it counteracts the vertical component of the car's weight and prevents it from sinking into the ramp. There's also frictional force that acts tangentially to the circular motion of the car, and this provides the centripetal force to keep the car moving in this direction. This frictional force would be directed towards the center indicated in the figure. Also, in the system schema on the slide shows these relationships, as well as the figure on the bottom shows a different situation where the car is going upwards after flying off of a ramp. This car then reaches its highest position and reaches its highest potential energy as a result, where gravity is then pulling the car downwards, indicating the magnitude of the final kinetic energy that is essentially the same as the highest potential energy. In order to investigate what variables impact the speed of the player as well as their acceleration, I designed a research experiment to go about doing this. My first goal was to find some data online that I could use in order to analyze, and I found 4 data sets from Kaggle for Mario Kart, including data for the tires, karts, characters, and gliders. I used this data in order to examine correlations and relationships using a combination of different Python libraries in order to display my results. I thought that a correlation heat map would then be a valuable tool to see how related some of my variables were, so that I could then hopefully connect these relationships to physics. Finally, I would be able to conclude from the results whether or not Mario Kart uses physics accurately and what these relationships are. As shown from this table, Dry Bowser is the heaviest character and shows the largest speed. Baby Princesses show the lowest weight, but also lowest speed. Dry Bowser has the smallest acceleration, and Baby Princesses have the largest acceleration. And from this, we can infer that there is an indirect relationship between acceleration and speed, and then a direct relationship between speed and weight. This indirect relationship between acceleration and speed, as well as acceleration and weight, can be seen in the equation F equals m times a, also known as Newton's second law of motion. The relationship between speed and acceleration in Mario Kart is consistent with the principles of kinematics, but does not necessarily directly relate to Newton's second law. If acceleration is higher according to the kinematic equation, the velocity would be higher for the same initial velocity and displacement. According to the kinematic equation, the relationship between acceleration and speed aligns with the concept that the characters with higher acceleration in Mario Kart can reach their top speeds more quickly than characters with lower acceleration. It's important to note that the game designers may use a combination of acceleration, top speed, and handling characteristics to create a balanced and enjoyable gameplay experience. Traction is closely related to weight when considering the interaction between a vehicle's tires and the road surface, and it also represents Newton's third law of motion. The relationship can be explained through the normal force, which is a force exerted by the system that is perpendicular to that surface in the context of the vehicle on a flat road. Traction is essentially the frictional force between the tires and the road surface. This force supposes relative motion between the tire and the road and is crucial for a vehicle's ability to accelerate, decelerate, and maintain control during turns. The frictional force, or traction, is influenced by the normal force. In general terms, the greater the normal force, which is related to the weight of the vehicle, the greater the potential for traction. During acceleration or braking, weight transfer occurs. For example, during acceleration, weight shifts to the rear tires, increasing the normal force and thereby enhancing traction on the rear wheels. Conversely, during braking, weight shifts to the front tires, increasing the normal force and improving traction on the front wheels. While a heavier vehicle may have a greater weight force, which can potentially increase traction, the distribution of weight among the tires and other factors, such as the tire design and road conditions, also plays a role in determining the overall traction. The variables that have the strongest correlation to speed, ground speed, air speed, water speed, and anti-gravity speed seem to be weight and handling, with handling having a strong negative correlation with a correlation coefficient around negative 0.84 to negative 0.85, with the weakest correlation being airspeed, and weight having a strong correlation between speed with a correlation coefficient around 0.84 to 0.96, with the weakest correlation being airspeed. The variables that had the strongest correlation to acceleration seem to be handling with a strong positive correlation between 0.8 to 0.93, with the weakest correlation being with water handling and speed, as well with a strong negative correlation between negative 0.72 to negative 0.94. So why may a higher weight make handling less effective? Well, heavier vehicles have higher inertia, which is the resistance of an object to change in its state of motion. This means that it takes more force to accelerate, decelerate, or change the direction. As a result, heavier vehicles generally have slower response times and may feel less agile when it comes to handling. Additionally, higher weight increases the braking distances. When a heavier vehicle is moving at a certain speed, it requires a longer distance to come to a stop compared to a lighter vehicle. This can affect the ability to control and stop the vehicle quickly, impacting handling in emergency situations. And although heavier vehicles may tend to grip more around turns, the vehicle may tend to lead more, also affecting the tire contact with the road, which can result in reduced grip and decreased responsiveness. So this plot shows the relationship between average speed for each driver body combination for the heaviest gliders. Gliders were essentially ignored because all of them had the same mass. However, they were all factored in here. For each character, the March Coupe Ink Striker seems to be the best for gaining greatest average speed for each driver, with Wario and Dry Bowser and Morton seeming to have the highest average speeds of 16. The Falcon and Buggy seems to also have the lowest average speed for each character, with it also being the lightest body. One might assume that this might also have the most acceleration. However, many other factors may influence acceleration, and the Landship and Streetle body is very close to being the same speed and is essentially the same weight as the Falcon and Buggy. The bar graph shows that the Landship and Streetle is much higher, as well as the Buggy and Scooty in terms of acceleration. This is likely because of their low weight profiles, as shown in the bar graph above. The Landship and Streetle seems to have the highest acceleration across all characters, with the Baby Princess and character of approximately 14, showing a downwards trend across all characters when the weight increases, as well as between the characters even when the cart decreases in weight. Additionally, each character has a relative trend across the cart, so it's pretty easy to rank the carts from being best to worst in general with addition to each driver. These trends then allow for later predictions, perhaps when they add new characters or carts, tires, and gliders when they're added in the future. So essentially, by using data analysis to examine relationships between variables that we explored in class as well, it is clear that Mario Kart does a great job of modeling physics. It might be helpful in the future, though, to look at traction more, though, because the heavier vehicles tended to have less traction overall, going against general physics concepts. However, this might make sense as a lot of the maps have turns, and the centripetal force might cause a larger vehicle to tip and have less traction. Considering physics concepts as well as this data, it seems like the best combination to play with speed would be Wario and Drive Bowser with the cart of March or Coupe or Ink Striker, and a glider that is a gold glider. On the other hand, if a player doesn't have much experience, it would be better to choose any of the Baby Princesses or Baby Rosa with a cart of Landship, Streetle, and a glider of Cloud, Parachute, Flower, Paper, providing for a better handling due to the decreased mass. So essentially, the conclusion is it is fictional.